Okay, so let's run through this dynamics question together, and what we have here is a kinematics question, particularly particle kinematics. So what we have here is a car is moving along a straight line with an initial velocity of 6 meters per second. When it is subjected to a deceleration, so it's negative acceleration, deceleration of a equals negative 1.5, the velocity raised to the power of 1/2 meter per second squared. And v here is our velocity, meter per second. So our acceleration is given as a function of velocity. So we want to determine how far does the car travel before it stops. So the way we can approach this question is using our kinematics equations in the FE handbook. So we're looking at the FE handbook 9.5 on page 77. That will give us the kinematics equations. And also in the new FE handbook 10.0, it's on page 115. So what do we have? Let's draw a picture real quick. So we have a car, and it's starting at what? What's the initial velocity? So we're given the initial velocity. So it's starting at some velocity, our v naught. I'm gonna call it v naught for initial of 6 meters per second. Then it moves, it moves, it moves, it moves, it moves, and it comes to a stop, right? What happens when a car comes to a stop? A particle or a car or whatever, it's zero. The velocity, our final velocity here is zero because it comes to a stop. So we're gonna use this value at the end. We just have to denote that when the car comes to a stop, anytime you see something come to a stop, the velocity is zero. That's always important. So we know that at this point it comes to a stop, and we want to determine how far does the car travel before it stops. So what's the displacement here? What's the distance? What's this distance? Let's call it s. How far does it travel? The s distance. So we want to find this. So let's begin, and I've stated we're going to use our kinematics equations. In the FE handbook, we're given the kinematic equations. So the first one is going to be A equals dv dt. Acceleration is the change in velocity with respect to time. Then we have the velocity is going to be, we take the derivative of the displacement with respect to time. Then the last one is going to be ADS equals VDV. So these are all given in the FE handbook 9.5 on page 77, the new FE handbook 10.0 on page 115. And the one we're going to use is going to be this one. So these are all with respect to time, and we know our acceleration is given as a function of velocity. So that's how I know I'm going to use this one, the third one, which is technically, when we substitute these together, we arrive at this. So this is just the extra equation that can be handy when you don't have that time variable. So we're going to use this equation, and we know what are we looking for. Let's go back. The displacement, right? We're looking for s. So we have a ds equals v dv. So I'm going to isolate ds. Divide a by both sides. These cancel. So ds equals v dv over a. And I know I can get s by taking the integral, right? So we're taking the integral. What you do here, you have to do to the other side. And now let's look at the bounds. So we're starting from what? What's the displacement? What's our initial position? Initially, we're at 0, right? So we start at 0. Then we're going to look at the final position, which is unknown. We don't know this. This is what we're trying to solve for. So we start at 0 here. This is where we end, s. That's the bound for the left side. For the right side, what do we start at? For the velocity, we're taking the integral with respect to the velocity. So we start at what? Initial is 6. So plug in 6. Final is some velocity that we don't know. This is unknown. So we don't know that velocity. So what do we do now? We do the integral both sides, and what you should get when you take the integral of ds, it's just going to be s for the left side. then we're doing the integral of v dv over a. But we know a, right? So we're going to substitute a on the bottom. So we know the value for a here. So it's going to be v, you take the integral, we have 6v, and a on the bottom, it's negative 1.5, v raised to the 1/2, and dv. We're integrating with respect to the velocity. So now we're doing that integral, but before this, I want to reduce this once more. So I'm going to reduce this further. So I know there's a 1 here, right? I do 1 divided by negative 1.5 is going to give me negative 0.6667. So it's going to be s equals, we still have the integral. I haven't done the integral yet. So we do negative 0.667. So this is this portion. That's taken care of. Then I do 1 minus 1/2. We have division. We have the same variable. So you just do 1 minus 1/2. And for that, you should get v raised to the 1/2. And we still have our dv here. So now I've simplified this. That's all I did here. Now we're going to apply the integral. So we're going from 6 to v. So the integral of this, it's going to be 1/2 plus 1. And that should give you what? 3 over 2. Then you divide the whole thing by the 3 over 2. So what this should give you, s equals to negative 0.667 v. You do 1/2 plus 1. We're taking the integral. So it's going to be 3 over 2. Then we take this 3 over 2 and place it on the bottom, right? So I can reduce this again. So I'm going to take negative 0.667 divided by 3 over 2. And that should give me negative 0.444. And it's going to be the velocity raised to the power 3 over 2. Then these are from 6 to v. So our integral is bounded. So 6 to v. So this is the initial. This is the final. So we do final minus initial. So if I do that, it's going to be s equals to negative 0.444. I take this v, plug it in here. It's just v. So that stays the same for the final. We're looking at that final of the bound. So it's going to be v to the 3 over 2 minus, don't forget that minus the initial, which is the 6. So I take the 6, plug it in for v. So you do negative, keep your negative here, 0.4446 raised to the 3 over 2. And this is, close that in parentheses. So now you can do the math for this, and you reduce this stays the same. So it's negative 0.444 v3 over 2. Negative times a negative is a positive. So we're going to get a positive. If you do the math for this, you should get 6.532. And all of this is in units of meters. So now we have the displacement, a function for the displacement with respect to the velocity. And if we go back here, what did we say about the velocity? So we're looking, how far does the car travel before it stops? We know when the car stops, the velocity is what? 0. So plug in 0 for the v. We just plug in 0 in here. And if you do the math for that, you should, this whole side should go to 0. So our answer should be just this portion. So s equals 6.53 meters. And that's the displacement before the car stops, and it should be d. That's all.